So we're just running examples of how to work with optimization and certain objective functions. So now let's see what happens if we take an 8-foot tall fence that is going to run parallel to the side of a house 3 feet away. We want to know what is the length of the shortest ladder that can clear the fence and reach the house. So as we want to see the shortest, here we want to minimize the size of the ladder. Let's assume that the vertical wall of the house and the horizontal ground are going to have infinite extent. So we have a situation like this. Okay, so we're using this ladder that is covering up of the fence and reaching the other side of the house. And we have this distance below between the house and the fence, which is 3 feet. And also we have the height of the fence being 8 feet. So now with this information, we can make a diagram as follows. We have the house here, and the house is going to be reached by the ladder at height B. This is the length of the ladder, which we call L, and we have the height of the fence, which is 8 feet, and the distance between the fence and the house, which is 3 feet. We don't know how much is going to be covered by the distance between the base of the ladder and the fence, so we're going to call that X. So with this diagram, notice that we can talk about some relationships for the house. And so notice that because we use a triangle, we can say that L squared is equals to B squared plus 3 plus X squared, which is what we get here, defining that relationship. Now, this is just a function for the length of the ladder. Next, we can use the similarities between triangles. Notice A is a V, like X is to 3 over X, 3 plus X. And so we get this relationship here between the two triangles. Let me just show you that in a little bit more detail. What we're doing is making a comparison on the two triangles. Which triangle, you might ask? Well, we're checking this is X and 8, right? And we have the big one, which is B, and we have the distance 3. So we can say, oh, okay, so this side over this side, X, 8 over X, can be 8 over X, is going to be the same that B over X plus 3. So notice is always the opposite side over the adjacent side. And we're comparing, since it's the same angle, this is the tangent, right? Is the tangent of the angle is opposite over adjacent. So is going to be both B over 3 plus X as it is going to be 8 over X. So this is essentially two representations of the same tangent of this angle. Now with that done, we can use this relationship to find what B is. And so we can do B is 8 times X plus 3 over X and replace that here in the equation. And that's going to lead us to an equation that only depends on X now. And then we can take derivative. We can take the derivative of L squared and find the critical points. So if we do that, notice that this is going to be a product rule with a chain rule. So we have that this is going to be 2x plus 3 times 1 plus 64 over x squared plus x plus 3 squared by the derivative of 1 plus 64x squared, which is going to be minus 128 over x squared. Now we simplify and factor a little bit of that, and then after simplifying, we obtain a more concise expression for the derivative. which can give us some critical points. So one of the critical points are going to be 0, where the derivative does not exist, -3, which makes this 0, and of course the cubic root of 192. Then after that, what we can do is just use any of the criteria of the first or the second derivative to check what of the values are going to work. Clearly 0 is not a value that we want because it's not going to make sense. 3 feet is too close because it's just going to be enough to cover this. So very likely the minimum that we can use is going to be the cubic root of 192. Okay, and just let me sure that that is actually the case. Notice that we can do the real line, minus infinity to infinity. We can put 0 here, we can put -3 here, and we can put cubic root of 192. Notice that it's also very easy to know that this is going to be the minimum value because this is nothing and this is a negative value. So at that point, we know that it gotta be this one. Okay? But now we want to confirm that this is actually a minimum value. So let's take an approximation of how much that is going to be. So we have 192. Cube root is going to be around 5.76. This is more or less that. So if we take some values here and here, we can determine the values of the derivative. So one value here can be 2, and one value here can be 6. We can take those values and plug them in the derivative. So notice L squared prime is going to be twice x plus 3 x cubed minus 192 over x cubed, right? So we take 2, that's going to be 2, and this becomes 5, and this becomes 8 minus 192, and this becomes an 8. So notice that very clearly this is a negative value. So over here, this is decreasing. Now L squared prime on 6. Now we have 2 by 9, and we have 6 cubed, and 6 cubed is going to be 216. Clearly that's bigger. 6 cubed here, but this is going to be positive. So notice that we have the change from decreasing to increasing. This is indeed a minimum value. And so with that, we can confirm that a cube root of 192 is our minimum for this. And so 5.76 is the minimum value that the letter needs to have so we can reach the house and still cross the fence. Now another example is we have a water storage tank in a small community that is built in the shape of a right circular cylinder. And it has a capacity of 32,000 feet cubed, so about 240,000 gallons. The interior wall and floor of the tank must be cleaned and treated annually, and labor costs for the cleaning of the wall are twice as high per foot square as the cost to clean the floor. So let's find the radius and height of the tank that are going to minimize cleaning costs. So this is the situation. We have this water tank, it has this radius, and it has this height, which are the things that we're interested in. And of course, it depends on the floor and the walls. So walls are harder to clean. So first, we're going to describe how much is the cost. Clearly, because we're talking about price, the cost is twice for the area of the wall, which is given by 2 pi r h, and the area of the floor is pi r squared. So we gotta multiply this for whatever the cost per square foot inch is. Okay. At this point, we have a restriction here, and is that the volume of this is going to be 32,000. So pi r squared by h is 32,000, and that's our restriction function. We're going to use that to get h, and so h is going to be in terms of pi r squared, giving us everything in terms of r. So I can replace the cost function now to be in terms of r. Once that we do that, then we obtain a function that we can take derivative. And when we take derivative and set the derivative equal to 0 to find possible critical points, we're going to get that r cubed must be 64,000 over pi, or r must be 40 over square root of pi, which is going to give me around 27.3 feet. We can also have the points where the derivative does not exist, but that's going to be r equals 0, and that doesn't make sense for an optimization problem. So we're only going to consider this critical point. By the theorem that we had before, since this is an interior point, this is going to correspond to the absolute minimum. Remember the stream value theorem. And once that we have this r, we can find what h is. And that's going to give us that r is 27.3 feet, and h is going to be 32,000 over pi r squared, which is going to be around 13.7 feet. So overall, the conclusion to the idea of the optimization is we set up a function, objective function. We use a restriction to put everything in a single variable. And then after that, we find critical points. We evaluate what are the possible maximums or minimums. And then we find the corresponding maximums or minimums for these problems.